All right, hello, welcome to the Off by One security stream. I've got a returning guest this week, Jonathan Ryder, who was on a few months ago, I think it was, talking a bit about command and control and how you can create your own custom one to hopefully get around endpoint protection and such. So I am not at my normal location. I'm in Los Angeles right now. I just did a keynote yesterday in Las Vegas for a security awareness summit, which is pretty cool. But couple of things here before we get started. A reminder that Hackfest is coming up in November and tickets are starting to move. So it's a limited number of people we can get in. It's in Hollywood. It's going to be a fantastic event. We've got, as you probably heard me tweet or say, a lot of great speakers like Chompy for day one keynote, Lena Lau for day two keynote. We've got Connor McGarr confirmed and Ruben Boonen. And we just now went through the CFP results and we did the selection of speakers. So we've confirmed the majority of them and that'll be coming out really soon. So excited to announce that. We've got people like Nahum Sek and Jason Haddix and other folks that are confirmed to come down. So aside from that, we have a bunch of great like IoT Village, custom CTF hacking, where you can win a SANS course as a prize, like lots of great stuff to share. So I'll be sharing more of that as we get closer to the event. Next week, my guest is going to, I think I have two individuals from BC Security coming on next week to talk about, it's called the Empire Strikes Back. These are the developers of PowerShell Empire, and they're going to be showing us some really cool demonstrations around what they're working on these days and some more cutting edge techniques. They've also got a class running next month in Las Vegas. I think it's in Las Vegas. Don't hold me to that, but it's somewhere. It's in person, and they're giving away a free seat during this stream next Friday. So if you want a chance at winning a free seat, you can either go in person and attend, or you can do it virtually. But you don't want to miss out on that one. So be here next week for that. I'm excited about that one too. So Jonathan, as some of you may be aware or not, is someone who works a lot within the Windows kernel and driver space and has a lot of experience. And that's, if you haven't gone into the world of the kernel and Windows, it can be intimidating at first. It's complex. There's a lot of pieces, a lot of massive structures. Like you may see small structures in userland, like the process environment block or the thread information block, and they're not that big, right? Then you look at something like KPRCB, the kernel processor region control block, and KPCR, and they are massive structures with hundreds of fields or members within it and nested substructures and unions and all the things. So that's some of what can be intimidating. But once you start breaking it down and you learn that at static offsets from the beginning of these various structures are fields of interest. Historically, things like previous mode is something quite interesting depending on the version of Windows that you're on. And there's this great project, which I've shared in the past, called the Virgilius Project. And Randall, if you're in the background listening right now, can you post that? It's the Virgilius Project. And that is a brilliant resource run by some individuals in Ukraine that shows every single Windows kernel version and every single structure and all the offsets within those structures. So if you wanted to do something like token stealing, but the version is Windows 11 and you've only ever done it on Windows 10 21H2, then you'll be able to go onto Virgilius and see the changes to the structure and which offsets are there so you can modify your shellcode when you're doing things like token stealing. So really cool stuff. I'll let Jonathan do a bit of an introduction as to what he's going to be talking about today with a life of a packet.
Hey, awesome. All right. Yeah, I got you. Can you hear me? Is it delayed?
Yeah.
Super delayed. All right, cool. Yeah, thanks, man.
There's a bit of a delay, but it's okay. Yeah.
Okay. All right. Cool. Yeah. So
maybe kill the camera for a moment.
Okay. All right. Bye, camera. So you saw me for a little bit. You know I exist. But in any case,
much better.
So cool. All right. Must be my camera taking up some of that bandwidth there. But yeah, so what I wanted to do for this stream, and I don't want to take up a bunch of y'all's time, probably about an hour, maybe hour and a half or something like that. But I wanted to do some education and jumping around the kernel side for the life of a packet. I know not a lot of folks dive into this really that much. I know many folks probably have experience using sockets, whether you're doing it in Python or C, like C sockets or Python sockets, or whatever the case might be. But you also have sockets in the kernel. Okay, so Microsoft, they have a lot of code samples out there on GitHub, and you can have kernel sockets, and you could do like, I think they have like an Echo client, Echo server example for nothing but kernel sockets. So if you're able to make that jump and try to understand a little bit more about kernel sockets, take a look at that code example and compile that and run it and play around with that. But I wanted to go just a little bit deeper with this stream. I wanted to understand, so like the past several months and up to about a year, I've been really trying to understand at the lowest level possible where that packet actually comes in. All right, so that's coming in at the NIC. All right, so Steve, if you want to turn on my share real quick, if you don't mind.
Yeah, and it's funny. I know that some people have heard me say this before, and I know, Jonathan, you have, but quite some years ago, I had a contract opportunity, and it was 3 months contract for basically the request was, we want to know exactly what Jonathan's going to talk about. Basically, what does a packet do when it enters the front door? And what if it's an IPv6 packet with these extensions turned on, but this one off? Kind of how does everything work? And that was a way bigger undertaking than I had appreciated at the time. So what I thought was a really good deal for me ended up being a really good deal for them. So
No, that's awesome. Yeah. So to kick it off, basically, I think everybody knows you have a NIC, right? You have at least one NIC on your system, and it can be attached to your system a number of different ways. Probably the most common way is attached to the PCIe bus. There's other types of NICs, but that's one I'm going to focus on for this one, right? I think that's just the most common one. In any case, so the NIC, okay, so the NIC, it's a slight little piece of hardware that you plug into the motherboard, and you really don't know exactly what's going on behind the scenes. Normally, you don't care. It just receives packets, it sends packets, it does just dark magic, and that's all that matters. All right, but let's dive a little bit deeper into that. I'll talk about it here for just a second because I can't do the actual hardware debugging on the NIC. But on the NIC, they have the ability to do a lot of things for you, more than what you might even know. Things like checksumming, doing like segmentation, packet steering, stuff like that can be offloaded and done directly on the NIC itself. That way, the system doesn't have to do any of that for you, and which is great because when it comes time to really care about performance, that is great because that's actually hardware, not the system side. So that's pretty cool. So this NIC, the NIC, they have some buffers. Okay, so at the hardware level on the NIC itself, they have some buffers. There is a buffer for all the packets that are going to be received on the NIC. Okay, so there's also the flip side of that. You have a send buffer, a transmit buffer, or a queue is what they call it. So these queues, you have a receive queue and you have a transmit queue. And there's typically a default size for these queues, and it kind of plays directly into the window size of a packet. A lot of times that window size scales, right? It's dynamically adjustable. And that is based upon how many packets roughly have been placed into the NIC's queue. All right, so when you're thinking receive and send, think about these queues that are there on the NIC itself. Okay, so that's on this little graphic that I made up here, my awesome little PowerPoint clip art. Down here at the very bottom level, right, we got the hardware NIC, okay, out there on the bus. And let's just say it's bringing in a packet and it has it in its queue. It's got like a stream or whatever, netcat connection, your C2 calling in, or who knows what, right? Doesn't matter. At some point in time, though, it's going to have to get to the system space and trickle its way down to the user mode application that needs that packet, needs that data, right? So if you have a Netcat listener on your host or whatever, it's got to figure out how in the world to get its way down there. So what happens is there will be something called a DMA, a direct memory access. So this is going to be a transference, if you will, a transfer of data that comes from the NIC directly into a system buffer in the kernel. Okay, so you have that buffer. That's a DMA happens, and you say, hey, kernel driver, a network driver like NDIS. Okay, so NDIS is kind of like the end all be all for all things packets that are coming in and that are going out. Okay, so it's going to help this transfer happen, and eventually they go ahead and it will get into that system buffer. Okay, then at that point in time, then there's actually the structure that is used to represent the data or the packet. Okay, and so these packets or the data that's coming in is represented by something called a net buffer. All right, so if I go to, let's go to Virgilius, and come on, here we go.
It's crazy when I first started looking at the packets in the kernel side of things. Like, first off, all that packet data is like in the various kernel pools, and there's pieces of it all over the place. But there's a WinDebug extension. The name of it slipped my mind. You probably know it, but it's brilliant because you can. There's another one that's not. I'll check that one out too. But you can say bang packet, for example, and give it a virtual memory address of a packet, and it tells you everything about it. It's beautiful.
Yes. I will show some of that here in a little bit. But yeah, so here we are in Virgilius, and Virgilius is great because it does have a ton of structures on here, except for this type of stuff. And I was like, oh man, you gotta be kidding me. You don't have NetBuffer stuff. Okay. All right. Well, whatever. So I fall back to MSDN documentation. So in this is a net buffer for what MSDN is going to let you see. Right? A lot of times on MSDN, they're like, this is an opaque structure. We're not going to show you all the fields or what all the fields are. They're reserved or whatever. So treat it as an opaque structure, yada, yada, yada. But in this case, net buffer is actually pretty well documented with all the fields within it. Okay. Which is very nice. Let me check out the comments here real quick. I think somebody had a question. Please share the command. Yep, we'll get to that here in a second. Do specific NICs have their own implementation within their associated kernel driver? So I'll get to that in a second of what actually drives the NIC. All right, so give me a second, and hopefully my explanation will help answer that question for you. But so we have this thing called a net buffer. This is how the kernel is, or NDIS specifically, is representing or describing data that is going to be either transmitted or received on the network. Okay, so you can see there's quite a few structures in here, so on and so forth. And if you're looking at here, like next net buffer, think of your CS degree or whatever, CS background, think a linked list. Okay, so you can also see here slist header link, net buffer header, some other important structures that may come of use to you when you're going through and you're trying to actually parse out and take a look at these structures inside of a kernel debugger session. All right, so a lot of times you'll have what's called this stream. Okay, there's a stream. Don't think of it like in Wireshark. Don't think of it like a TCP stream, UDP stream, HTTP stream. Don't think of it like that. All right. So in Wireshark, if you're looking at the dump or you're just capturing, sniffing some packets, you look at some stream, you right click on it, and say follow TCP stream. Okay, that's not what this really is referring to. Okay, so a stream is basically just a connection from one socket to another socket. Okay, so for example, this browser tab that I have open right here for MSDN documentation, this is one stream, if you will. And then in another tab, I have a completely different stream. And these streams are not going to cross each other, right? We're not going to cross streams or do anything like that. And it has to be that way, right? You don't want your streams to be crossed, especially if you're doing some banking or some day trading or what have you. You don't want other tabs or other streams to know what other streams are doing, right? That could get kind of nasty, right? So that's being separated out, okay? And that separation happens with net buffers. And furthermore, net buffer list. Net buffer list can be a chain, like a net buffer list. Call it net buffer lists. All right, so you can get really crazy really quickly trying to understand all this stuff. Net buffer lists, and net buffers, and all the links down in them. Okay, so at some point in time, though, the kernel is going to have some kind of, let's say, inspection to take a look at what's inside of a stream, to say what's inside the data, what's inside the packet, to do inspections right there to see what the source port is, destination port is, local IP address, remote IP address, and actual raw data. All that stuff will be located within this. Okay, so then what happens is Endus has certain logic that we really don't care about right now. That will go ahead and start to parse it further out to say, hey, is this TCP version 4? Is it TCP version 6? Is it inbound? Is it outbound? Is it HTTP traffic? Is it ICMP type stuff? Okay, all of that is happening, right? And if I can jump into a debugger real quick, I can kind of show you some of these debugger commands.
Yeah, I posted the one that I was trying to find before. It's CMKD. It's from the Code Machine folks.
Oh, cool. Nice.
Yeah, check it out. It's a nice one.
Okay, so what I have is a kernel debugger session with 2 different VMs. Right, so I will say that when you're doing like kernel level stuff specifically for networking information and NIC stuff, there's a big difference from what VMware lets you do to what Hyper-V might let you do, and actually looking at the hardware itself from 2 physical systems. All right, so depending on how what you're trying to see, how low level you want to go, maybe VM to VM is not the best bet. You could do a physical machine to physical machine, or at least Hyper-V. All right, so one of the things that we could do to check out some of the network adapters or some of the mini port drivers that could be installed on your system is we have this extension. This extension command is called endus-kd. So endus-kd we'll go ahead and show you all of the attached network adapters, the drivers behind the scenes, the mini port drivers behind the scene. So real quick, so terminology like mini port driver, what the heck is a mini port driver? The mini port driver is what is responsible for driving the actual NIC. Okay, so all those DMAs that happen, everything that is going to happen from receive queues, transmit queues, all that behind the scenes that come in the form of these mini port drivers. So if you do endus-kd.help and if you do a -verbose, you can see just how robust this extension command is. Okay, so lots of things to take a look out here. We're not going to go through every single one of these. It doesn't matter. We don't care about all of these. But if you are a network programmer or a mini port developer or whatever, and this is your day in, day out, you'll probably become very, very familiar with a lot of these commands. And you'll navigate yourself in the kernel pretty good, I would imagine. So one of the things that's kind of cool with Endis, with this extension, is it's cool to go ahead and explore all these commands one by one. We'll do that here for just a little bit, but one of the things I found is really cool. It just takes a long time to do it. All right, I did this yesterday, and it took about an hour to generate this. It's a report. All right, net report. So endiskd.net report, and it says draw a box diagram of your network. All right, so let's take a look at that. I did this the other day, right? So I said it took a long time, but this is that box diagram of my system or my network as it is right now. Okay, I mentioned this is just a virtual machine. Okay, so it says that there are quite a few mini ports here. All right, so WAN mini ports, so on and so forth. If you hover, you can go and click on some of this stuff, and it'll go ahead and give you some really good detailed information about that particular mini port. All right, so this is basically a nicer way than having to click through, run through all those commands all manually. This is a one snapshot, one summary of when I ran this. Okay, so net adapters. You can see we're here at the net adapters tab on the summary, and we see all of the mini ports that are here. Okay, we have the Microsoft kernel debug network adapter. Okay, that's what I'm using for my kernel debugging session. I'm using KDNet. All right, KDNet, I think it's pretty popular. It's really fast and it's very easy to set up. I think there's a few others as well. Virtual KD maybe was one. There was another one. I don't know, Steve. I don't know if you remember the other one that's out there. Drawing a blank on that one right now.
Virtual KD is the one that I pretty much always used until they stopped supporting it.
Yeah. Yep. But see, does it use ASCII art to create? No. It made this diagram. It made this, right? And it's not just like ASCII art. It's everything is clickable. Well, almost everything is clickable, right? Which is pretty sweet. Okay, you can see if you hover over this, the blue stuff is like makes you think you want to click that one. All right, so you can click on the KDNet one. All right, so all these. Oh, okay. Edge, just go ahead and crash on me, huh? Can't handle it. Okay. Let's go ahead and try back up.
Did you take 760 a while back when we used to do the kernel debugging of the TCP/IP.sys driver?
No, I don't remember that piece.
Before the more recent version, we used to debug TCP/IP.sys and look at some specific vulnerabilities that were like denial of service bugs and such. And it was neat because we use a lot of these tools. But one thing I was able to work out, which is really cool, is get a heap spray in the kernel pool by using a packet vulnerability, or not packet vulnerability, but driver vulnerability. It was the one where you could keep the FinWait2 state forever hanging open, if you remember that one. And basically, the vulnerability was if during the teardown sequence, when you send a fin to the target system, no, I'm sorry, when you are on a system like SSH connection, for example, and you say quit, it's the server side that sends the fin to you. And when you respond back, you set the window size to a 0, and it forever keeps that specific session in a FinWait2 state. And you could just spray with hundreds or thousands of packets, and it would start filling up the kernel pool and end up being all adjacent memory. So you could do some heap grooming in the kernel pool with a packet spray and fill up the packet content with your, NOP/SLED, shellcode, whatever you're trying to do there. And it was a nice way of getting kind of a past ASLR in the kernel when it was not too ridiculous with 64-bit. It was great.
That's awesome.
RCE bug. Yeah.
Yeah, no, that's pretty cool. I think you had Chompy on not too long ago where they talked about something similar, another vulnerability in something TCP/IP.sys.
Yeah, it was a DOS. Yep.
It's all about how all these different drivers and stuff are handling all these packets that get passed down from Endis.
There was one that was discovered not too long ago. It was privately disclosed, but it was a remote code execution TCP/IP.sys driver bug. So flick a packet and remote code. If you find one of those, that's a 7-figure bug right there.
Oh yeah, absolutely. All right, it's all fileless. That's beautiful stuff. So back to this output here. So net adapters, the KDNet net adapter here. Again, this is just an overall summary of some of the manual commands that you could do with NDIS KD. All right, you can see the overall state of this particular driver. Okay, yeah, it's running. The interface is up for it, right? So it binds, attaches to interfaces, yada, 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 the flags, PNP flags, so on and so forth. What's kind of cool here, the power management piece. All right, so y'all might be familiar with Wake on LAN, right? So it's nothing new, right? It's WOL or WOL, Wake on LAN. And this particular section right here, power management. All right, so for Wake on LAN to be enabled and ready to receive that packet, your NIC can't be completely obviously shut off, right? There has to be a certain amount of power going to the NIC because it has to be able to process that Wake on LAN packet. And so this is going to dictate what the power state is going to be or what the power state was required for that NIC. Okay, so you can see we have these different device state levels, and they're kind of tied to a system state level for power management. We see a hibernate and a shutdown. All right, so when you're thinking of Wake on LAN, you can see how it's actually not enabled, not set up for this system. All right, but what's happening here, it's going to go into a device power state of D3, and the NIC is going to have a little bit of power to go ahead and look for these Wake on LAN patterns. So if it's parsing through these packets and it sees this one packet coming through, which is basically just a MAC address repeated over and over and over and over again, forget how many times it is, but in any case, that's going to be like, oh, hey, that is a Wake on LAN packet for me. Let's go ahead and wake up. So we'll go ahead and wake up the system, bring everything back online, and it's going to do whatever it needs to do. Okay, so that's kind of cool. All right, so you have a various number of what we call protocol drivers. Okay, so you can kind of see the different protocols that are supported, most popular being TCP, right? TCP/IP version 4 and version 6, okay? And these will have what we call handlers. Handlers are the drivers, are there functions out there that will go ahead and, no kidding, handle, let's say, the transmission of a packet or the receiving of a packet. Okay, so we can see that inside of TCP/IP. Let's see if I can zoom in a little bit without Edge crashing here. There's a handler that will be invoked or gets called for whenever a net buffer list has been sent out and is completed. Okay, so where that is implemented inside TCP/IP is FL. So FL, right? So a little bit of background knowledge for Windows APIs, user mode and kernel mode. A lot of times they have a prefix of some kind to let you know kind of what it is, what it's referring to. Okay, so FL on the kernel side of the house is referring to the framing layer, right? So it's a framing layer API, and this one is send net buffer list chain complete. There's also one for receive. Okay, so I'll show you what it looks like when we do a breakpoint on that here in just a bit. Okay. You can see all the ones that are currently open and some more details about these particular protocol drivers. You can see the handlers, where they're located, and specifically where it is, what's attached to, so on and so forth. Okay. Filter drivers, don't need to jump into all that yet. Interfaces. Okay, so all these interfaces are present on this particular VM. Okay, all these interfaces can be virtual. They can be Wi-Fi. They can be Bluetooth, right? You see Bluetooth device here. KDNet is here. And then this one, this is my actual NIC. Okay, so a lot of times you'll see, yeah, here it is, 802.3. It'll show you the media type, the physical medium for what it is, the alias. Okay, so the interface alias, okay, Ethernet 0. The burned in or the baked in MAC address for this NIC, and the interface index. Okay, so each one of these interfaces is going to have its own index, going to have its own GUID, and all those things are used to pull packets from and send packets out to. And just some other details about the overall state of it. Okay, you can check out the summary to show you just at a very, very high level of what the report can look like. Where was this report generated? This report was generated inside of Windowbug. All right, so go ahead right here. Endis KD. All right, so bang Endis KD. And if you do .NET report, doesn't like tab completion for some reason. NSKD.net report. Okay, that's how I generated that HTML page. And again, word of caution, that can take upwards of an hour depending on your system resources, and all what's going on there.
What would you say is the biggest value from that report?
So I would say for me, it saves me from having to run a lot of these commands individually to see that same data. Right. So if you have the time, maybe you just let that report run all night, and you just wake up in the morning and take a look at the results and be like, all right, cool. And you can go ahead and just interactively explore around and look at the different things. All right. So I'll show you an example using Endis KD. All right. So NDISKD.net adapter will only show me the adapters. What? Get out of here. I have a typo? Huh. Weird. Must have had a typo or something. But in any case, so in that summary, we saw all the network adapters that were present on the system. Okay, so that information is gathered or retrieved by using NDISKD.net adapter. Right, so you'd have to go through and manually go and issue a bunch of these NDISKD extensions and the sub extensions, the sub commands like dot something to get that same amount of data. Now, if you wanted to actually dive deeper into a net buffer structure to look at the data possibly in a packet or in a stream, you can't do that inside of that net report, right? And it kind of makes sense, right? I guess it's going to be way too much data, and there's so many packets flying through at a time. Like Windows is a very, very chatty system. There's packets coming and going all the time, telemetry from going to the Microsoft mothership, all kinds of crazy things. So it would be way too busy and be way too large of a report. All right, so you can see all the net adapters here. And what's nice about Windowbug Preview, or actually it's not Preview anymore, it's just Windowbug, and there's Windowbug Classic. You can click on a lot of this stuff. It's all clickable. It's really nice. Okay. So you can see some of the same information that we saw in the net report. All right, but what we can do now, since we're actually live in a kernel debugger session, is we can go ahead and click on things like the actual driver itself. We can look at the state history for this particular device if we wanted to. We can look at the bindings if we like, and like the Endis lightweight filters that are present. But what I like to do down at the very bottom, more information. More information, you can see if there are any packet filters, receive filters, anything specific for the actual NIC itself, any Endis ports, the wake on LAN stuff. Okay, and of course it's not enabled, so there's definitely nothing going to be there. And then any pending net buffer lists or any pending NBLs that might be coming in or might be going. All right, so let's take a look at some of these handles. These handles for this KDNet. All right, so KDNet represented by Katie Nick. All right, Katie Nick has implemented quite a few NDIS handlers. Of interest would be the send net buffer lists and also return. All right, what you could do is go ahead and just click on the BP to go ahead and set a breakpoint for that. Okay, looks like I already had one there because it says breakpoint 0 has been redefined. So a BL, just do a listing with a breakpoint. Okay, and so if I go ahead and I just fire this off and I just say F5, let it run, boom, we get our first hit. Okay, it says breakpoint 0 has been hit. Katie Nick, MP, send net buffer lists. So if you are familiar with the prototype or the signature of this particular API call, you'll know what register has a pointer to the net buffer list. All right, because it's 64-bit, obviously a lot of the arguments are going to be in registers, RCX, RDX, R8, R9, then the stack. Okay, so for this particular API call, I know that RDX holds information that I might want to take a look at, and that is going to be the net buffer list. Okay, so what you can do is with another NDIS command, you can say bang NDIS AD, right? And then NBL, okay? So NBL is a net buffer list. And I say at RDX. Again, so RDX is holding that net buffer list. Okay? Those are the results for the NBL. Now, one thing that's really cool with this is you can go ahead and force it to walk the entire chain of NBL structures. You can also dump the data that's inside of this. And you could also go ahead and show this as a Wireshark hex dump. Okay, so you grab the hex dump from this, and what you could do is you can copy and paste that out, open up Wireshark. You can open up, I think there's an option to open up a raw hex dump or something in Wireshark, and it'll go ahead and apply its filters and all the things that it knows and disassemble, make sense of this dump. So you can see exactly what that packet looks like. It's really sweet.
Are you able to, with that breakpoint, can you specify like a conditional breakpoint that allows you to specify which IP address, like, you know, that kind of a filter on there?
There is a possibility to maybe do that. You'd have to start diving down into all the MDLs that are attached or that are inside the net buffer. It's possible. It'd be very convoluted, I think.
Yeah. Well, like you said, like as soon as you hit F5, bam, you hit a breakpoint, because that's such a busy spot to break. So if you can't set a condition, I can imagine that'd be a nightmare after a while.
Yeah.
It's
yeah.
super
Like
cool, though.
I can't even just hit an F5, just hitting go. The system won't even go. Like every time I hit it, it's just getting a breakpoint. But yeah, let's see if I can just go ahead and
there's a queue of a million packets now waiting. yeah. But you can see here, for example, all right, so this is an interesting one. All right, so inside this net buffer, just doing a dash data, we have a couple of things, a couple packets, if you will, inside this stream. You can see here test VM.local. Okay, so the test VM is my other VM that I am attached to. Excuse me. So you can see some of the different types of packets or some of the different types of traffic that's coming from my test VM. Can we generate a PCAP that we open up? Like, I don't think, at least not to my knowledge, I don't know of a window debugger extension that will go ahead and dump out the entire MBL chain as a PCAP. If that does exist, I don't know about it. If you happen to find it or know it, let me know, because that'd be kind of cool. Yeah, that'd be really sweet. Yeah, so, all right, so that's how you can inspect some of these individual packets that are inside of a stream. Okay, so we're looking at a net buffer that's been created, right? And inside we have this MDL's memory descriptor list where actually the data resides. Okay, MDLs are kind of cool. So MDLs is a very interesting structure and it's a cool idea. So
and RAM, right? In RAM, you have your physical memory, and a lot of times these packets and the headers of the packets could be in various parts of physical memory. MDLs, they can help abstract that away and say, hey, guess what? I am going to distort your view, if you will, and say that you are now looking at a virtually contiguous chunk of memory, right? So even though something could be completely scattered across physical memory, MDLs can basically just say, nope, everything is contiguous. That's all you need to care about. Oh yeah. If you do find that, that'd be sweet. That'd be really cool. All right, so let's flip over just a little bit to the coding side. Okay, so let's say that in a particular scenario, Conor McGar was on your stream a while back there, Steve, and he talked about some ways to go ahead and get into the kernel, get execution, talking about some primitives, stuff like that. So see his talk if we haven't seen that talk or that stream. That was awesome. And so going along that mindset, all right, so let's say you found some kind of read-write primitive to go ahead and load your own vulnerable driver or what have you, bring your own driver to the game. I would implore you to go ahead and try to create what's called a WFP driver. All right. If you're able to create this Windows filtering platform driver, one of the things that you can do is you can have full control of what packets come in and leave the system, which can get pretty nasty. One of the things that you can do is, off the top of my head, you can do proxying. Okay. So if your implant is out there trying to beacon out somewhere, and you have your WFP filter out there, you can say, oh, okay, Mr. Beacon, I see that you're trying to go here, but actually that's not where I want you to go. Let's go ahead and redirect you over to somewhere else, a different C2 infrastructure or what have you. Okay, so it's pretty cool. It can do redirecting, you can do proxying, stuff like that. You can also go ahead and look at the contents of the data in streams. Okay, so again, these streams, a stream is basically just a socket connection from one end to the peer end or to the remote end. Okay, that connection is one stream. So you can go through inside of that stream and inject all kinds of crazy things into it. You can take things out of it. You can drop a packet. You can drop an entire stream. You can deny permissions. You can deny people the permission to even bind to a packet. If you see somebody trying to open up a netcat listener and port 4444, you can say, no way. Or you can say, it's like, instead of doing 444, let's do 31337.
Like burp proxy, but advanced, right?
Yeah, absolutely. Yeah. All right, so let's flip over to the code side real quick. Let me see. I think I need to disable this. Let's let that thing go. All right, there it is. Cool. So what I have here is a WFP driver. Okay, so this is a call out driver. A call out. So what the heck is a call out? All right, so Endis and a filtering engine. There are two different types of filtering engines. One is the BFE, all right, the base filtering engine that is inside of that resides in the user space. User space has the BFE and think the Windows firewall. If you ever open up the GUI for the Windows firewall and you're making rules and stuff like that, you are using the BFE and WFP APIs and stuff like that. And it's very powerful, all right? Very powerful. WFP can be present and is present in user mode and kernel mode, right? The beauty to being in the kernel to make a WFP filter is the ability to inspect the data of a stream of interest. and to mess around with that. You can manipulate it all day long. You can drop it. You can inject things or whatever. Okay, you can only do that though in the kernel. All right, so this call out. Right, so call out is going to be basically, let's say, for lack of better words, a callback, if you will. So the filter engine inside the kernel, anytime a packet is coming in at a different layer, let's say like the framing layer, transport layer, so on and so forth, the IP layer. Kind of get the idea. There are these different layers, and at each layer, it'll go through and say, all right, I'm going to look at all call out drivers and see who wants a callback, who wants to be represented with the data for this stream, because let's say you want to do some inspection. Maybe in the realm of EDRs or antivirus products, they are absolutely doing this. Defender has an NDIS filter, WFP filter, to do this as well. Kaspersky does this. I think Bitdefender might as well. There's plenty of security products out there these days that are doing this stuff in the kernel. Right, so they can catch those malicious packets by doing inspection of the packet or of the data for a stream and saying, this is looking pretty suspicious. Let's go ahead and reject that connection. No way, you're not coming in here. Okay, so super powerful stuff. All right, so call out. Okay, there's a crap ton of code here. We got just shy of 1,000 lines of code. All right. We're not going to go over all 1,000 lines of code. All right. That's going to take up way too much time. Okay. Let's go back up to the top here. All right. So whenever you're creating a kernel driver of any kind, you have different routines that are required to be there. You have a driver entry and a driver unload routine. The driver entry is basically just the entry point or like the main function for the program. Okay. Driver unload. Okay. So when the driver is about to be removed, deleted, uninstalled, or whatever, driver unload gets invoked. Okay. And then I just have some wrapper functions about opening up a handle to the filter engine and doing some registration for my callout driver. Okay. So these prototypes right here, flow, delete, notify, and classify. These are other, let's just say callbacks or other routines that can be invoked by the filter engine based on certain actions happening at a layer of interest. So for example, flow delete. Something is about like a stream, if you will, or what MSDN is actually calling a flow. When that is going down, this can be invoked to say, hey, guess what? This is being torn down. We have sockets being terminated, destroyed, or whatever. We want to give you some information about it and show you the layer ID for it, the ID for the call out, and any context for that particular flow, if that's of interest to you. There's also this notify routine. So whenever a new filter is being added, a WP filter is being added, this notify routine of every single driver that's been installed and registered will get their routine invoked, and it'll pass through. It'll pass you 3 parameters here: the notify type, the filter key, and the actual filter. Okay, if that's of interest. But the big one, the meat and potatoes of creating call out drivers, is a classify function. You can see all the parameters here. And within this, this is where we can do all the crazy things I was mentioning before. This is where we can do the actual inspection of the data for a particular stream or a flow. Okay. And there's also some metadata that the filter engine will go ahead and create and add to particular streams. All right. So go ahead and show you a little bit more of this code here. My driver entry routine is just setting up some basic things, creating a device object. creating a symbolic link, and then specifying a couple of future things I would like to do if I have some more time to expand upon this. Being able to create like a communication port to allow user mode communication, stuff like that, to have any kind of further impact or control about this WFP callout driver. Okay, and then right here, this is where the registration of the callout itself is going to take place at this layer, right? So internally, there are some constants that can specify all different types of layers, right? These constants are basically just these GUIDs, as you see here, for what you might be interested in being called for. All right, so we will go ahead and register our callout driver at the stream layer for version 4. Okay, there's version 4, there's version 6, and so on and so forth. There's outbound, inbound, transport stuff, so on and so forth. You can explore this header file all day long if you'd like to. If you get bored, you can't sleep at night, they'll put you to sleep real quick. All right, so that's not the function of interest. It's supposed to go to the register. F12 didn't work for me for some reason. Let's try it one more time. F12.
How hard is it to get something signed these days if you wanted to get this signed?
Oh, man. You got some money? You got some money too? Yeah, I mean, there's SigThief and there's some other tools out there to go and steal some stuff, steal some certs or whatever. It's pretty difficult. You got to send all the stuff to Microsoft and they do some testing. You got to verify everything. And there's a lot of tests and like unit test cases or whatever that your driver has to go through, and they'll either reject it or approve it, obviously, and they'll sign the driver and give it back to you, and away you go.
I miss the old days.
Yeah, right. Well, it's very, very expensive, very time consuming, very annoying. All right, so this register call out. Okay, so there are just a crap ton of structures that are involved for this. Right, and then inside these structures, this is where you can go in and actually see the data within a stream. Right, so to get things started, one of the things that you have to do is you have to grab a handle to the filtering engine. And if this driver was created for user space, like a user mode driver, it would go ahead and grab a handle to the BFE, right? That filtering engine. And then, but obviously this is a kernel mode driver. So the handle to the engine that it's going to grab is the kernel mode filtering engine. Have I done this for Linux? No way. No way. I'm not going to be touching Linux at any point. Yes, I do hate Linux. Yeah. Yep. You will not find me developing any code or any kind of kernel driver for Linux. No way. I don't know, just a tangent on that. Like, why in the world? Why in the world would I spend all my time and effort on Windows? I don't know. I like pain, torture, right? So Windows is like this giant black box, especially in the kernel. I can't go out to GitHub and see the source code behind something like malloc. Linux, obviously it's out there. You can go ahead and see all that. You can see all the source code for GitHub and all that for the kernel. Cool. I don't know. It's an extra challenge. I don't know. What do you think, Steve? Why do you do some Windows stuff?
Market share, the value return.
Yeah. Yeah, exactly. Right. So pen testing, red teaming, that type of stuff. Right. More often than not, the majority of systems that you're going to see in organizations is going to be Windows. Right now, I know there are some companies that are issuing out Macs and say everybody has a Mac. Right. So maybe that's something I need to think about. But yeah, Windows through and through. But yeah, so back to code here. All right. There is a special structure that I called my kernel call out, right? What it is basically the FWPS call out structure. If I hit F12, we see where that is, and hit F12 again, go to header file. or where this is implemented. We see inside of this, we have a callout key, we have some flags, a pointer to a classify routine, pointer to notify routine, a pointer to a flow delete routine, so on and so forth. Okay, so all I'm doing here is going through and initializing this particular structure. Okay, because what I'm going to do is I'm going to go ahead and register this call out, okay, with the filtering engine, right? And we'll say, hey, go ahead and call FWPS call out register. You'll see a lot of times these structures and these APIs, they have different numbers appended to the end, and that's basically letting you target different versions of Windows. You can see like 0, 1, 2, 3 can be used for like the most recent version of Windows. All right, so if you want to go back to as far as possible for FWP or there's too many acronyms. There's FWP, there's WFP, and there's WPF, right? Not to be confusing at all. All right, so if you want the most kind of portability, if you will, use like the zeros, the 0 for structures, a 0 version for APIs, so on and so forth. All right, so you register the call out, and you go ahead and store that. I'm storing that inside of a global variable. You could put this inside of kind of structure or what have you, whatever you want. All right, so if that's good to go, we'll go ahead and proceed on to our, I would say, user mode structure. Reason why I'm calling it a user mode structure, user mode call out, is because FWPM, anytime you see something prepended or prefixed with FWPM, that is available to you as a user mode component, user mode application. Anything with the prefix FWPS, that is for system space. That is a kernel structure or a kernel mode routine. All right, so we have FWPM structures, we have FWPS structures, we have FWPS APIs, and FWPM APIs. Okay, so in any case, go ahead and I initialize that FWPM structure. Say, hey, here's my callout key. Here's my display information and the layer of interest that I want this to be applicable to. And go ahead and I call FWPM call out add 0 to go ahead and add my call out. Okay, you need to pass this one the handle to the engine. Look at that little doggy. Doggy's learning about some kernel stuff. Yeah, so you call it out. You call that call out. Yeah, call the call out routine. Okay, so that gets added, and then we go ahead and create a GUID or user ID, a UUID for the sub layer. Okay, so calling this API here, X UID create. Okay, there's other ways you could do this. UID gen is one way. You could also, I'm sure there's a website that'll do it for you online. Okay, so I'll go ahead and create that, and I initialize my sublayer structure. Hey, I just give it a name, a description, the GUID that we made for it, the weight and the flags, and then we go ahead and add that sublayer. Okay, FWPM sublayer add. And then the filter piece. This is where all the fun really is. Okay, the true power, if you will, of WFP callout drivers is within the filter. So we have a filtering condition. And I say you have to have a filtering condition because you don't want to be notified of every single packet on every stream because you're just going to bog down the system. There's no way you're going to be able to keep up and make decisions about every single stream or every single packet that's coming in. Don't do it. All right. So what I'm doing here is I'm creating just one filtering condition. You can have a number of filtering conditions. I'm saying here that I am going to look for the port 31337. Okay, that's my local port of interest. And this is the type for it. It's an unsigned int. And I want a straight up equal. There's other things you could do. You could do a greater than, you could do a less than, you could specify different ranges if you want to say, hey, ports 0 through 1024. I don't want anybody who's not elevated to make sockets for or whatever. You can do all kinds of crazy stuff. Okay. And then this field key. This field key, if I F12 this, just another GUID from the FWPM header file. And it's saying this is the local port. Okay, so you specify that inside the structure. Say, hey, I'm looking for this local port. What port? 31337. And we're looking for a straight up equal. Then for once we have the filter condition done and all filled out for what we want, we can go ahead and take that and add that to our filter structure, not to be confused with the filter condition structure. Okay, so we have this FWPM filter. We have a layer, right? The key to layer, FWPM layer stream 4. Okay, so looking only at version 4 specific streams. The GUID for it, for the sublayer, the GUID for the filter, the name, description, the GUID for the callout, so on and so forth. Okay, and we just say, hey, there's only one condition so far, and this is where it is. Once you have that all filled out, you go ahead and say FWPM filter add. All right, and then once you're all said and done doing all that stuff, everything's been added, the callout's been registered, so on and so forth. You don't need the handle to the engine anymore, so go ahead and close it. 870 in alpha. I wish 870 was in an alpha stage right now. I am creating content for one if I get the green light to make one. And this type of stuff is going to be in Security 870 if all the planets align and everything goes according to my plan. Yes, there will be a 770 and 870 someday, some year, who knows.
So I was saying just skip 770, just go straight to 8. It's good.
Yeah, absolutely. Yeah, we can totally do that. But yeah, this type of stuff is going to be 870.
When you're like in this driver, I'm assuming there's a real easy way to do it. But like, say for example, you know how when you're doing debugging, you can use JavaScript, use a math ATAN function, set a breakpoint, print things out. Like, can you set something up in the driver pretty easily so kind of you know where you're at and you're forcing a break at a certain condition, or do you just have to set a breakpoint on the driver once it's loaded and when a filter hits?
Yeah, multiple ways to do it. So I know there are a lot of folks out there that say, we don't believe in printf debugging, meaning I would want a bunch of printf statements to kind of use as debugging to see where you are in the program or whatever. I don't care. I'm all for that. You can see here, I'm using kdprint and some other wrappers around it. There's also, debug print. There's so many different printf, if you will, in the kernel to have inside every driver. So I use quite a few different versions, if you will, of like a printf. So kdprint, just a macro, it expands out to debug print. There's also debug print X to specify different levels of the message, so on and so forth. I'm all for it. Every time a function or whatever is being called, I have a kdprint saying, hey, we're entering in this particular function. And then when I leave, I have another one that says, hey, we're out. We're done. Peace out. So yeah, I love having that, right? If I'm not seeing certain messages, then I'm going to go ahead and dive in a little bit further and be like, I expected this routine to hit or expected this routine to finish all the way through. What's going on? Then you can do something like debug breaks. You can go ahead, break into the context. There's a particular driver, set breakpoint in the driver or whatever. There's multiple ways to do that. But I start with the easiest, and that's just a bunch of like printf statements. But yeah, long-winded answer. All right, where was I?
Fair enough.
Yeah. All right. So call out registration. Okay. So call out registration has been done. We added the filter, we added the sublayer, we created the filter condition, and we registered the actual call out, right? We specified the classify routine, notify routine, flow delete routine, so on and so forth. Unregister just does the opposite. Okay. Nothing to see there. Now, inside of my classify routine, So here we go. Classify routine. All right. Have my printf debugging statements, my KD print. I have this one wrapper, this wrapper function, or just the utility function, if you will, called decipher network information. So inside of infixed values, we have this structure here, right? So you can go through and see the information that's coming into your system, coming into the NIC. Okay, so incoming value, you can F12 that, and you can see what's there. We have a value structure, FWPS value, and you can see we have tons of different types here, types of values. All right, UNT32s typically will be holding your IP address, right? So it's not in a dotted decimal format. You will have to convert that. All right, your port numbers will be UNT16 and UNT64. I believe that's for IP version 6. I think it's either that or it's a byte blob. I forget off the top of my head. In any case, so one of the first things that this classify routine is going to do is decipher the network information. What is coming into the system? So decipher, you can see here I have a switch. I got this switch statement, and I'm switching on the layer ID. And I said, hey, is this the stream version 4? And it better be, because that's what I set it up to be. That's the only thing I was interested in. Okay, there's other ones you could do, right? Version 6. You can look at datagram information, datagram for version 6, inbound transport, outbound transport, so on and so forth. And just look how ugly, look how nasty you have to get inside of this, right? So if you want to grab, let's just say the direction, is this in, is this out? You have to come in here and say classify value, then the structure. Let's grab the incoming value, specify version 4 direction. So field stream packet version 4 direction dot value dot uint16. And say, is this inbound? Yeah, if it is. If not, it's the other way. All right, then to grab your local IP address, okay, you got the dot value dot uint32. You got to convert that into something more print friendly, if you will. So I have another helper utility. Convert uint32 to dotted decimal format. Okay, it doesn't do anything fancy. It just converts that uint32 to dotted decimal. All right, but you see it's very, very annoying to go ahead and dive into all these different fields to access that data. All right, but that's just the pain that you love to do if you're diving into kernel debuggers, kernel drivers, and callout drivers. All right, so that's my decipher network info. All right, back to my classify. We do that. Okay, so classify, we have our layer data here. And the later data is where the inspection can actually happen. So layer data, inside of this structure, it has a member called stream data. The stream data is the no kidding data for the stream that we want to take a look at. And so what we could do is, for the actual stream as a whole, we could say, I want to block it, drop it, or let this continue. Or, we're not going to take any kind of action, let that go ahead and proceed on. Okay, we're not interested in the whole stream. We want to pick out little bits and pieces of data inside the stream. Okay, so one of the things that you'll have to do is you'll have to copy any kind of the data from this stream into a local buffer. All right, and then FWP, they give you a very nice API to go ahead and copy that over for you. Okay, then at that point in time, that is where you go about and do your inspection in the data and do whatever you would like to do. Okay, you could go ahead and swap it out, replace a word, replace if it's HTTP gets, you could flip it to be HTTP put, post, trace, whatever. Maybe you strip out an iframe. Maybe you have some kind of driver out there to strip out all invisible iframes that are coming in, right? You can do that. You can do that here. This is that point in time where you do that. If you want to inject invisible iframes with some malicious JavaScript, send it somewhere else. You can do that here. So much potential, so much power of what you can do at this point in time inside your driver. Okay, so enough of explanation of code. Let's go ahead and show you a very, very lightweight demo of kind of like what's happening when this code runs. All right, so just going to minimize that. Got my debugger back up and running. All right, inside of my test VM.
And is this up on GitHub or is this private?
No, it's not anywhere right now. Kind of keeping it private to see if there'll be a lab inside of 870 someday. But if you do want to take a look at some of this code, it's basically just following examples from MSDN GitHub. Right, so there are tons of examples on their GitHub repo. They give you examples of how to do inline edits of streams. So any kind of modification of the actual packets, you can go and do that there. They show you how to do all of that stuff, right? So that's all the driver is basically doing, just little minor tweaks here and there. All right, so on my test VM, all I've done is use an SC utility to go ahead and call SC create to go ahead and create this, and SC start to go ahead and start my WFP callouts. All right, now if I go over to the debugger, you can see my fancy printf debugger statements, right? So driver entry routine hit. We registered a call out. We got our handle to the engine, and looks like we already hit our notify routine. Notify routine said, hey, a new filter has been added. Well, yeah, that's us. We did that. All right, so it's passed. And then everything is just closing, right? Close the engine, close register call out, close driver entry. Hey, so driver's there, up and running. Netcat, because we were specific on port 31337, go ahead and start listing on that. All right, and nothing's happened yet. Okay, so there's no data there. It's just a port that's been bound. Okay, so no data whatsoever has gone to that particular port. So we go ahead and we can connect to that. Okay, so we have that initial connection, but no data is there yet. Okay, because, so how do I know that? Well, I have printf statements. Now go ahead and decipher that network information that's going through that particular stream. So let's go ahead and send something over there. Let's send security 870 over there. All right, so it went through. We can see that on the other side. Yeah, it's just a netcat chat. Cool. Now look at this. All right, so my classify, the classify routine has been invoked by the filter engine, and it says, hey, there's a version 4 stream, the direction it's coming into our system. The local IP is this with the local port. Yes, that is accurate. That's what it is. That's what we're trying to do, a match equal on that port. The remote IP obviously is that on the remote port. Okay, we can obviously verify that because I did a -v, a netcat, and it says the remote port is 64359. Yes, 64359. And it's saying, hey, the data buffer that you might want to start looking at some point in time is located here. Okay, so what we could do is, I'll go ahead and break this. And do I still have this? All right, cool. I went ahead and re-enabled this. Let's see if I can do this quickly. All right. I think this might be mine. I don't know. DX at $cur process. Ah, look at that. Okay, cool. Netcat.dxe. All right, so remember, the net buffer lists for this particular API is at RDX. So if I up arrow a little bit, where is it? RDX data. Okay, cool. So you can go through and start to manually, if you wanted to, which is just very boring, very time consuming, try to inspect all of these packets that are going in and out of the system. Okay, so F5 again, right? Nothing much there. Oops. You don't do data. Let me show you this. Right, but don't do data. You can go ahead and click on walk MBL chain. Right, it says, hey, this is where the first net buffer is located, is the context for it, where the current MDL is, where the first MDL is, the data offset, right? Data offset. Where is the actual data found from within this particular structure? Right? If you click on MDL, you can see all the data within the MDL, what the MDL is representing. So hit 5. And you can display as wire strike hex dump. We took a look at that. Same thing, pretty much same thing as dump payload, except here it's making the offsets pretty much nice and perfect for Wireshark to go ahead and ingest. All right, so if I take off the data, I'll walk the chain, just to show you a little bit of that. Right, really nothing there. Okay, cool. So what you can do is, inside of your driver code, you can go ahead and inject text into it. You could try to do some encryption of stuff. You could decrypt stuff. You could look for anything that's been base64 encoded or whatever to take a look at that to say, hey, you know what, this is suspicious or whatever. Anything that's going out, you can go ahead and base64 encode it or do other things on its way out at the kernel level. And maybe, I haven't tested this yet, it's on my list of things to do. Maybe there are certain things that you can hide from Wireshark. Right? So if Wireshark, it has a driver as well, right? It has a driver sitting in the kernel. It's looking at all this stuff. Perhaps there is a way that you can blind Wireshark so it won't see some of these packets, or at least some of the data of these packets that are flowing through. All right. So if that works, cool. I'd like to jump on the stream again and show you how that could, how we could possibly blind Wireshark or something like that from a host perspective. From a network perspective, which is net sniffing or span ports and stuff like that on Cisco devices or whatever. Good luck. Good luck trying to fool that type of stuff. But yeah, so that's in a high level, if you want to call high level inside of a kernel, kind of like the life of a packet, if you will. All right, there's a lot more deeper things you could do. You could follow the packet all the way down to Netcat, or all the way down to your browser to make sense of how a packet is, or how a stream and data in a stream is transformed to HTTP. That way browsers can see it and stuff like that. But yeah, so that's pretty much it. That's all I got.
Yeah, that's pretty low level stuff. It's pretty awesome. Yeah, I mean, like, it shows you the power too, like being able to write these drivers and just, I mean, you can do so much. Once you've got a template like what you have right now, you can go in and do so much with it. So it's pretty neat.
Yeah, like that's just the potential, like the tip of the iceberg. Okay? Yeah. There's so much that you can do. There's basically just limited by your creativity of what you want to do, and maybe limited by your knowledge set of Endis APIs and stuff like that.
What would be, in a few sentences, like how you would approach hiding something from Wireshark? Like, what would that look like?
So my initial idea of trying to do something like that, just theory at this point, is trying to better understand what altitudes or weights that those drivers might have. So if you think of file system mini filters, they have these altitudes, and if you're above somebody or below somebody, you might see more than a lower level driver, or you might see less than an upper level driver. Right, so that's what I'm wanting to test out in theory, is if there's kind of like an altitude, if you will, for WP filters to see where Wireshark is. Can I be above it? Can I be below it? Can I change what it sees?
Yeah, for sure.
So
that's interesting.
Yeah.
I'll look forward to seeing what you find out there. That'd be cool. All right, sweet. Well, thank you for coming on and sharing that. I'm definitely going to be bugging you in the background for a copy of that, because I don't want to go and redo it myself.
Yeah, no doubt. Yeah, it takes a minute.
But, Yeah, I'm just thinking of all the ways, like, how you would approach making things like exploit development a little bit easier or more possible, having this knowledge and this control and power and just being able to like see things in the middle. I think at a minimum, just having the ability to write a driver dealing with something like TCP/IP is going to get you a lot of the knowledge you would need to then begin to start coming up with ideas as to where you would approach looking for vulnerabilities. Because like how I found them in the past was mostly dumb luck. Like a couple of the ones that I
Yeah.
found in a TCP/IP driver it was just luck, and it ended up being something that's exploitable. Again, as I said earlier, if you can find a remote code execution bug in TCP/IP.sys, like it's absolutely worth 7 figures. Now, there's different types of buyers out there, of course, and you got to be obviously aware of who you'd be selling something like that to. But that would be an example of a true server side type vulnerability where no
Yeah.
user involvement is required. Like you don't have to worry about firewalls for the most part, depending on where inside the driver it gets triggered. But I mean, once you also branch out into, as I was saying as well, like what if this extension is turned on? For example, you're doing source routing, or what if you are using ESP or AH within IP version 6 because it's an extension built in at layer 3 as opposed to being shimmed in between the layers. So all those different directions that things can go and take, it's intense. It's an extraordinary amount of code.
Yeah. And like, so more to the point there. It's like the wake on LAN stuff, right? The wake on LAN had like a magic pattern within it.
Yep.
What would stop you from having a kernel driver in there looking for a magic pattern for your C2 packets, right? So you're going through and you're inspecting all those, you find your little magic pattern, that's your C2 stuff. And like, oh, this is my C2 traffic. I'm going to go ahead and do something special for this. Strip off that magic byte or the magic header, if you will. Send it somewhere else. Send it to a different application so the browser doesn't get it. Maybe your beacon gets it or whatever. Right? It's insane what you do and what Microsoft lets you do inside of this level. It's incredible.
Yeah, absolutely. And anytime a new attack surface is introduced, then that's obviously a great place to look. I mean, it's still the case where, remember when IP version 6 came out and all these different vendors out there implemented part of the stack, but not with support for all the extensions because they were rushing to get it out there because they thought that IP version 6 was going to take over. And then as we know, IPv6 is pretty much on by default with all operating systems, and there's all kinds of cool ways to get around things, but there's still got to be a ton of vulnerabilities. You think about the maturity of IP version 4, and we still today find things that affect and that have been there for 20, 30 plus years. With IPv6, there's still so much in there waiting to get discovered. So,
yeah, absolutely.
Question for you.
I want to grab a link to some MSDN code here just to show you guys. Zoom in a little bit. Oh, too much. All right, so you can see on GitHub, right? So Windows 8.1, the WDK, WFP stream edit sample. Okay, that's basically where a lot of this code was based off of right here. Right? They go deep into the weeds of streams and the data within the streams, what you can do with it. You can transfer it, you can proxy it somewhere else, you can reject it, you can reject certain ports or whatever, you send it to a different port, all different kinds of crazy stuff. Real quick, what I'm thinking about too, there is, I forget the name of this VPN, but there's an open source VPN, it's like soft open or something like that. Their code's out here on GitHub. So if you want to see how this VPN provider is creating a WFP callout driver, take a look at that. See how it's doing some VPN stuff by the way of a kernel callout driver. Does Windows support XDP?
Yeah,
Not familiar with that acronym, XDP.
Yeah, XDP. I don't know, like desktop protocol type stuff, maybe. I'm not sure.
Yeah, maybe.
But cool. All right. Well, let's wrap it up there. I appreciate you coming on again. Great information.
Yeah.
This is of course being recorded. Express Data Path. I'm not
not
familiar with Express Data
familiar.
Path.
Yeah, not familiar
Personally.
Yeah.
Yeah,
How
I
could I
mean,
use this to fuzz?
fault injection
Uh,
would be really easy to do with this. Yeah.
Oh yeah, yeah, absolutely. I mean, I guess from a fuzzing perspective,
So,
you could go ahead and manipulate all the packets all you want. Put in some bad garbage in some of these fields for some different headers inside of a packet. But I mean, there's no point. I don't think there's a point to really do that in the kernel. I guess if you're trying to fuzz an actual kernel driver, right? Trying to fuzz an actual driver, use Scapy. Use Scapy, craft up some of those packets from the raw, create some malformed packets, and send it off and see what the driver does. See how it handles it. I think it was soft ether.
what's the name of that? Soft ether. Okay.
I think so.
Cool.
I don't remember off the top of my head.
All right. We'll close it out here, but again, appreciate you coming on. Next week, again, we've got the folks from BC Security coming on and talking about PowerShell Empire and what they're working on now, and they'll do some great demonstrations, as well as giving away a free seat to the class they're running next month. That is a $3,000 seat. So if you want a chance at winning that, definitely come back next week. Otherwise, have a great weekend. Thanks again, Jonathan. We will see you next time.
Thanks.